In this module, we will talk about the 7 instruments of quality. These instruments are designed for people with little knowledge of statistics, to give them a number of handles with which they are able to determine whether a certain deviation in the quality is either a coincidence or has a specific cause. There are 7 instruments. We have the check sheet, the histogram, the so-called Ishikawa diagram, a flowchart, the Pareto Analysis, the control charts, and the scatter diagram. We're now going to discuss them one by one and see how they can help us as project manager. In this production line, we see 3 machines. The operator of each individual machine keeps track of when there is a failure. He does this very simply by adding a dash on a card attached to the machine. This way you can see which machine has the most disturbances. How can this help you as a project manager? You can count the number of errors in the delivered subsystems, but also how often certain team members somehow manage their work package to deliver on time or too late. In short, the list is a very simple way to keep track of how often a particular event occurs. This is much better than the impression that remains in your memory after some time. Similar to the previous instrument is the so-called histogram. Here, the height of the bar displays how many times something has happened. As you see, it gives you the same information as the check sheet. The only difference is that this is a graphical image. Now suppose that you have come with the previous techniques to the conclusion that at some part of your project too many mistakes are made. The Ishikawa diagram, also known as the Fishbone Diagram, gives you a handy tool to check for the possible causes. The Fishbone Diagram is actually a cause breakdown structure. In this example, there are 8 categories where you can find a possible cause. There are several fishbone diagrams available, depending on the type of problem you have or the type of industry where you're in. Here you can see the highest decomposition, but each branch we are going to decompose in more detail in order to find the root cause. Let's see how this works. In this example, I have broken down one of the legs of the fishbone. The example I use is the leg of the employees. I have broken it down into 3 main branches: inexperience, chemistry, leaving the project. And leaving the project, we have broken it down even into more detail. The lowest level of the fishbone diagram, we call them leaves. Now this diagram, the Ishikawa diagram, does not give you a solution, but it gives you a probable cause. Once you're behind the cause, then you can think about where to find your solution and how to implement this. Another means to search for the cause of potential problems is the flowchart. It gives you an overview of a certain process. You can examine each component of your flowchart and see what possibly can go wrong, and how you can organize the process in a more efficient way, in a more qualitative way. The Pareto analysis is a way to prioritize problems. It works like this. You make a list of all the areas where there are errors, and you quantify these. Then you arrange this list from the highest to the lowest ranks so that those areas with the most impact in terms of finances are at the top of the list and those with the least impact at the bottom. This will be reflected into a histogram. You then determine the percentage of each part of the whole and then cumulate the percentages. Then you make a second graph you draw over the histogram. After that, draw a line from the cumulative percentage axis and select the first 80% of the problems. These are the areas where you concentrate on your first go. After you have resolved them, you then repeat this process until finally all errors are gone. Here you can see the list from our previous example. You see that we initially focus on redesign, rejected products, unclear specifications, and warranties. Is this useful for a project manager? Suppose you have delivered an ICT system and are in the testing phase. There is limited time available for conducting all the tests. Using the Pareto Analysis would give you the opportunity to focus on these errors with the most impact, on those subsystems with errors that have the highest priority. The Pareto Analysis helps you to calculate this priority. The following instrument, the so-called control chart, is simple in its use, but to understand exactly the background of this instrument takes some time. The chart contains a number of observations which somebody has done on a given product. The question now is, do we have a problem or not? Are the large deviations from the average quality defects, or is there a coincidence? Because that is also possible. Let's see how we can use the control chart for determining this. Here we have the 10 different measurements that were plotted in the previous chart. Imagine they are the installation times of something. It is up to the project manager to decide if he has a problem. As you see, all these measurements are distributed around an average. Each measurement is actually a part of a larger statistical distribution. There are now two possible causes why a particular measurement deviates from that average. The first is what we call a common cause, when it's just coincidence, when everything falls within the statistical distribution, within what is expected. Statistically speaking, there is nothing to worry about. It is also possible that there is a specific cause. That's when I cannot prove that these deviations are within the statistical distribution. That what we are seeing in the measurements are so improbable that there must be a problem. Statistically, there is something wrong. So we have to look for the cause of it. So when we have a common cause, if it is a coincidence, the only intervention is to perfect the process. When there is a special cause, we need to look for the problem, to find the cause, and to solve the cause. The first thing you do is to create a chart and plot the measurements. Please note, this is not yet a control chart, but a so-called run chart. The control chart, we will see, needs some more information to give you an indication about the probability of these different measurements. What we have already seen is that there is a variance in the different measures. They are distributed in a certain way. This variation gives a good indication of the process quality. That is not to say that you don't have the process under control, but it is less accurate. We can see 10 different measurements with an average of 253. Let's calculate the variance of these different measurements around that average. We do this in the following way. The first step is that we subtract the average of each measurement. This is the column that you now see. minus 12, minus 20, etc. It is tempting to add all these numbers as a measure of the variance. But because there are negative and positive numbers in this set, this will probably count up somewhere around 0. We can solve this by calculating the square and divide that by the number of measurements minus 1. The number that you get is the so-called variance. Now you can say, because we've got everything squared, this is not a good measure. Well, we then draw the square root of this number, and this will give us what statisticians call the standard deviation. Variance and standard deviations are beautiful measures of the dispersion around the average. For the enthusiast, I put down now the mathematical formula in calculating the standard deviation. With the standard deviation, we can do interesting things, because when the number of measurements above and below the average are almost equal, so when the distribution is symmetrical, we can say that the measurements are normally distributed. The normal distribution has some interesting features. We can say that in the area between one standard deviation above and below, approximately 68% of the measurements will fall. Between two standard deviations below and above, this number will be 95%. And between three standard deviations above and below the average, 99% of all the measurements need to fall. With the control chart, we can now demonstrate whether the measurements are probable. That is something we are going to investigate in the next slide. We now draw lines on the charts that we have just created. Our run chart is reshaped into a control chart. First, we take above and below the average a distance of 3 standard deviations. These are the red lines, and these lines are respectively the upper control limit and the lower control limit. We know that over 99% of all the measurements between these two limits will fall. This is one of the properties of the normal distribution. When the upper control limit and the lower control limit fall within specification, that is to say within the so-called upper and lower specification limits, we can say that our process has adequate quality. When that is not the case, we need to improve the quality of our process. The team members draw the control charts. Over time, they are going to study the different patterns. Some patterns are so unlikely that as they occur, that is a good indication that there may be a specific cause and that there is a problem not yet identified, but that should be resolved. Let's look at what kind of patterns they need to look. The first is when in a series of about 7 measurements, 2 measurements are above or below the upper control limit and the lower control limit, it is so unlikely that there is probably something wrong. We have the following pattern when more than 7 between a standard deviation above and below. Also, this is very unlikely. The third pattern, we see a kind of alternating pattern, up and down and up and down. That too is unlikely. In the fourth pattern, we see 7 on a row above the average. Very unlikely. When there are 2 in a row above 2 standard deviation, it is also a very unlikely pattern. The rising trend in this 6th chart is also very unlikely. Even then, there's something we need to worry about. If you look at the 7th chart, you will see that there is a whole series of measurements always beyond a standard deviation above or below the average. This quantity makes it very suspect and so very unlikely. At last, we see a set that successively is more than a standard deviation of the average. Unlikely, and therefore also gives an indication that there might be something wrong. What does the control chart? It gives us statistically an indication that there might be a problem. Finally, we have the so-called scatter diagram. This is a tool that can help you to identify a correlation, to discover a link between two data sets. When we see the number of errors versus the time when the errors are made in this chart, it is clear that as you progress during the day, people will make more mistakes.